Last time our detector answered a different question than the classifiers before it. Not just what's in the image, but where. It drew a box around the thing and said, "It's right here." Now we take one of those boxes, a crop with text in it, and ask the hardest version yet. Not what kind of thing this is, but what does it actually say? This is OCR, Optical Character Recognition, and it lives squarely in the predict stage of our pipeline. But notice the output has changed shape. We're not predicting one label anymore. We're predicting a string. This is the moment vision starts handing off to language. Here's the shift in one picture. A classifier looks at an image of a cat and says, "cat." One image in, one label out. But an image of the text B8X2K isn't one label. It's 5 characters in a row, and the next image might have 4 or 7. The answer is a sequence, and we don't know its length ahead of time. That single change, variable length sequence out, is what makes OCR its own beast. So, how does a network read? The same way you do, left to right. Think of the image as a strip of paper. If we slice it into thin vertical columns, each column captures a sliver of whatever's underneath it. Some columns sit on the left edge of a letter, some on the middle, some on the gap between letters. Reading becomes walk across those columns in order and call out what you see. The convolutional stack does the slicing for us. As the conv layers shrink the image, they leave behind a feature map that's short, a little tall and wide, and that width axis lines up with horizontal position in the original image. Each step along the width is a column of features, a learned description of what's happening at this horizontal slice. We've turned a 2D picture into a 1D row of feature vectors. Vision just became a sequence. Now we need something that reads sequences, and that's exactly what an RNN is for. We send those columns in order into a bidirectional LSTM. Bidirectional matters here. To know whether a stroke is the end of one letter or the start of the next, it helps to peek both ways. So one LSTM scans left to right, another scans right to left, and they pool what they learned at every column. Here's the problem that nearly killed OCR for years. The network produces a prediction at every column, maybe 40 columns, but the answer B82K is only 5 characters. Which column is the B? Where exactly does 8 begin? Nobody labeled that. We only know the whole string, not where each letter sits in pixels. CTC, Connectionist Temporal Classification, is the trick that makes this not matter. It lets the model propose a per column guess and figures out every possible alignment that collapses to the right answer, then trains all of them up at once. CTC's secret ingredient is one extra symbol, a blank. Not a space, a blank. It means no new character here. So when the same letter spans 5 columns, the model can say B, 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 and the blank lets us know those are all the same B, not 5 of them. And between 2 real letters, a blank marks the boundary. That one token is what lets a 40-column readout shrink down to a 5-letter word. Decoding is the cleanup. At inference, we take the most likely character in each column. That's greedy decoding. Then 2 rules. Collapse runs of the same character into one, and then drop every blank. So BB8 8x2KKK becomes B8x2K. That's it. The raw per column babble turns into a clean string. And that's the bridge. We started with raw pixels and ended with characters. Actual language the rest of a system can use. From here on, the input to our models won't be images at all. It'll be text. Which raises the very next question. How does a computer turn a word into a number it can do math on? That's exactly where we're headed. Let's build it. One file, 3 pages. We load the CAPTCHA images and build a character vocabulary. We assemble a model that goes conv to reshape to BiLSTM to dense logits with a CTC loss baked in, and then we train, decode greedily, and measure how close the reads are with edit distance. Every line is on screen. Follow the gold box. Page 1 is data. We read the PNGs and crucially we pull the label straight out of each file name. The captcha b8x2k is literally saved as b8x2k.png. We build two little lookup layers with string lookup. One maps characters to integers, one maps back. We deliberately keep index 0 as a reserved slot. That's the slot CTC will use as its blank. Then a tf.data pipeline decodes each image to grayscale, normalizes it, transposes it so width comes first, because width is our time axis, and pads the labels, batch it, prefetch it, done. Page 2 is the model and this is the heart of it. Two conv and pool blocks bring the image down and fan out the channels. Then the line that does the magic, a reshape that folds height and channels together and keeps width as the sequence length. That's our row of columns. Two stacked bidirectional LSTMs read it. A dense layer over the vocabulary gives us logits per character at every column. And note, no softmax here because keras.ops.ccskillos wants raw logits and does the log softmax itself. Then the keras3 idiom, I wrap keras.ops.ctc loss in a small layer that adds the CTC loss during training with add loss. So the model takes two inputs, image and label, but predicts characters at inference. We compile with Adam, no loss to argument, because the CTC loss was already added inside the model with add loss. Then model fit for a handful of epochs. Watch the loss fall, it starts around 19, and by the last epoch it's down near 3. That fall is the model learning simultaneously what each character looks like and how to align its column guesses to the answer, without us ever telling it where a letter sits. Inference. We build a prediction-only model that stops at the logits layer, run a batch through it, and call keras.dobson.ctc decode in greedy mode with mask index zo. That does the collapse and drop blanks we talked about, and it hands back sequences where blank and padding show up as -1. We clamp those to 0, map the integers back to characters, and we've got strings. To score them, honestly, we don't use accuracy. One wrong letter shouldn't fail the whole word. We use edit distance. How many single character edits to fix the read? tf.edit distance gives us a mean of 0.21, about one slipped character for every 5 codes. For 5 character captchas trained from scratch, that's a model that genuinely reads. And there it is, a network that turns a smear of pixels into the letters b8x2k, convey to see, LSTM to read, CTC to align, greedy decode to clean up. The output of vision is now language, but every character we just produced is still a symbol, and a neural network can't multiply a letter. So next we go to the very foundation of every NLP model in this course, how words become numbers, text vectorization and embeddings. That's where the real fun starts.